Thanks, Hamri. Okay, so yeah, the plan is to talk about Kirillov orbit method for certain Pro-P groups. The Kirillov orbit method started with Kirillov in the 1950s, where he used the method to classify and construct irreducible representations of nilpotent Lie groups. And then in the 70s, it was adapted to Pro-P groups and to certain nilpotent groups in a very nice way. And that's the story I would like to tell you. But the audience here is quite diverse. I don't want to assume a lot, so I will start with giving the background of what I think is needed to understand. So today, it's going to be a refresher on profinite groups. So let me start with something which I will need throughout my talks, and that's the periodic integers, or the periodic numbers. So a norm on the rationals is a function to non-negative reals, such that it is multiplicative and subadditive, and say non-trivial. Example for a norm is the regular absolute value, but there's also the p-adic norms. So p-adic norm defined as follows. So the norm of a number we'll take out the p power from that rational number. So now x tilde has no p power, neither in the numerator or the denominator. And the p-adic norm of this number will be 1 over e to the r. And it is easy. I mean, this is clearly replicative. It's easy to check that it is not only that it satisfies the triangle inequality, it's also an ultra norm. So this norm satisfies that x plus y, the p-adic norm, is less than the maximum. So, for example, if we look at sequence the numbers p to the n, then the norm of p to the n is 1 over p to the n. So these numbers, they converge to 0 when n goes to infinity. And so we can use this norm to define a metric on Q. So the metric will be d of xy is just the norm of the difference. And then we can complete the rationals with respect to this norm. We get the p-adic numbers. Inside the p-adic numbers, we have the p-adic integers, which are the completion of integers with respect to this norm. So let's see how it looks. So the completion, we can describe it as follows. These are infinite p-adic expansions from A0, A1p, A2p square, etc. But we continue up to, we allow infinite expansions where the AIs, they are between 0 and p. So p to the n goes to 0, and so whenever you take an integer and you start adding, expanding it and adding more digits, they become smaller and smaller. And so this is exactly the form of an element in the completion Z. And if you look at the completion of QP, then you will have denominators. So this expansion will start with negative powers. So an element here will start like a minus n to the n for some n, and then it will have some infinite expansion. Now, as a completion, we get that Z now embeds densely in ZP, and one can show that ZP is compact and Hausdorff, and totally disconnected. Sorry? Please ask. Yeah, I'm taking, so this number here does not have any p power. Well, it's a rational number, a over b. Neither a nor b will have a p power. Yeah. Okay, we will actually, later on, we will prove these properties. Sorry? We will prove these properties. We will revisit the p-adics, but I need them for a starter. Now, also, this is a ring. You can add and multiply, and it is it's a local ring. So as a ring, it is local. Is the unique maximal ideal. So what have we done here? We took the integers. They have no topology, and they have so many ideals, and we embedded them in a compact ring. So now we have a topology, and the topology behaves well. It's Hausdorff, and it's totally disconnected. And we also reduced the number of ideals here. And this is a very powerful tool to study that came into number theory in the previous century, where you can embed the rationals inside QP. And in fact, just a remark, if you look at Q, so we mentioned the usual absolute value, where we complete with the usual absolute value, we get the real numbers, where we take the two-adic numbers. I forgot to say that P is a prime. So cannot be otherwise. So you can take the two-adic norm, and then you embed in Q2, etc., Q3. And in fact, these are all the norms, possible norms on Q, and that has been a major theme in number theory and representation theory, local global principle study, the rationals in terms of these equations. In fact, this is not only a compact space or topological space with good properties. This is an example of a topological group. And I want to talk a little bit about topological groups. So G is a topological group. It's a group, and if it's topological space, and if they're happy together, they communicate well. So that means that, so it's a topological space, it's a group, and the group operations for multiplication and inversion, these are continuous. And it's not difficult to check that, that QP, for example, is a topological group. Operations are continuous. Okay. In the world of topological groups, there is a family of groups with prominent status. This is in terms of applications, in terms of how we find them in nature in the broad sense, and in terms of the theory that have. So, and these are the locally compact groups. So the group is locally compact if it is locally compact as a space. So that is to say, every point in the group has a neighborhood with a compact closure. So that's the definition of a locally compact space. And we also, embedded in the definition, we ask it to be Hausdorff. So it's a locally compact space, which is also, it's a locally, it's a group, it's a topological group whose topology is locally compact and Hausdorff. And the reason that these groups have such a nice structure is that they have a How measure. So, for example of such group are the real numbers, and in fact also the periodic numbers. So if you take element in the periodics and you shift the element A with, you take the coset, the additive coset with ZP, that's a compact set, a ring, whatever, but it's a compact set. So you get a neighborhood of A which is compact. So QP is also locally compact. And in the real numbers, we have the Lebesgue measure, which is invariant under translation, under the group operations. And that's a feature that any locally compact has. So if G is locally compact, then it has a How measure. So that's a measure on the Borel subsets, sigma algebra of the Borel subsets in G. So we're taking all the open sets and we generate the smallest sigma algebra. And for every subset in sigma algebra, and every element in the group, we have that the measure of GE is the measure of E. So it is invariant under translation. Now, in the real numbers, this is a commutative group, so we didn't worry about left and right. Now we need to worry. So this is a left How measure. So this is the sigma algebra generated by the open sets in G. So we need to distinguish between left and right How measure. So it has left How measure and it has right How measure. So we just need to pick a side. Let's take the left. And really, the How measure allows one to transport ideas of harmonic analysis from the reals or the circle, whatever groups one is used to this general locally compact groups, of course, with enormous complications because not complicated. But I want now to descend to the compact case. So if G is compact, then there exists a unique How measure with the property that the measure of the group is 1. And it turns out that this How measure is both left and right invariant. And right. And we will be soon interested only in compact group lectures. But before I kind of go completely into compact groups, let me say that in general, if G is locally compact, you can look at the connected component of the identity and turns out to be normal, a subgroup, and it is normal and it is closed. So one can write down the exact sequence of topological groups. And now this part comes totally disconnected. So I want to remind you that the totally disconnected, it means that the only connected subsets are the singletons. So this is the connected component, and this one becomes totally connected. That will be my abbreviation for totally disconnected. And since I started with locally compact, then that property also inherited by this group. So this is totally disconnected locally compact group. And in this theory, this group is known to be approximately a Lie group. So that has to do with the solution to Hilbert's fifth problem. So for every U open in G0, there is a compact normal inside U such that G modulo K is isomorphic to a Lie group. So to begin with, we don't require that G has any structure of a manifold or like this. So we cannot expect that it is a Lie group. But it is isomorphic to some Lie group. But this is not the part we'll be dealing with. We are going to deal with these groups. And specifically in the case where G is compact, or these are. So we'll be dealing with compact Hausdorff and totally disconnected topological groups. And here's a definition. We call it definition 1. Group G is called profinite is compact, Hausdorff, and totally disconnected. It's one of the definitions, one of the equivalent definitions of a profinite group. But this doesn't tell us a lot about look like and hides the reason for the name. So let's go in that direction now. Okay. So to get the other definition, I need to introduce the inverse limit. So that's going to be somewhat long definition. Do it slowly. So let I be a directed set. So this is a partially ordered set with the extra property that for every two element, I and j, in I, there exists a k such that k is greater than I. And given a directed set, I want to look now at an inverse system. So this is a directed set. And now I want to look at the inverse system. Of whatever you want. Sets, groups, rings, you decide what do you want. These, so sets, groups. Now what does that mean? It means that for every I and j, such that I is less equal to j, there is a morphism phi ij goes from gj gi with the property. So again, morphism in whatever you made your choice here. So now you stick to it. Function or ring homomorphism or group homomorphism. With the property that firstly, phi I is the identity. And these morphisms are coherent. So we have I less than j less than k, then phi, get the order right, so gk goes to gj I. Then we want phi ij ak to be k. Okay, I didn't start the definition yet. This is the setup. And now I want to find the inverse limit. So the inverse limit of the system is going to be a subset of the product. So I'm looking at the product. I want to define a subset product. So elements here, they will be, well, vectors here, with the property that phi ij of gj is gi, or I. Okay. These are coherent tuples, elements. And this is the inverse limit. Let me just remark that it solves the following universal problem. So suppose you kind of draw all your subgroups, all your groups, rings, whatever, and you look at the diagram that you get here. And suppose you have some group H. Okay, this is the universal property. So if you have a group H with morphisms into all these groups, such that all the diagrams that you get here are commutative, then there exists a unique morphism. So I can look here at the inverse limit The inverse limit also has maps, just the projections to all of them. And by the very definition, these are commutative grams. So there is a unique morphism such that everything now is the diagram. That is to say, the inverse limit is the closest object in whatever category we are to that diagram. Everything else that maps into this diagram and commutes with the arrows must say hello to the inverse limit. Okay. I think this is okay. No? Please object if there is an objection. It's better that you tell me now rather than I tell mistake. Okay, so for example, there's another definition of ZP. You take set the inverse system will be Z modulo e to the I. Z, and you have the canonical morphisms from Z modulo Pj to Z modulo Pi for I J. And the inverse system, the inverse limit of this system, ZP. I mean, long way, but if you think about the way we defined it here, then this sequence is compatible when you chop it backwards. So an element here, you can think about it as compatible sequence over there. So you need to work a little bit, but that's another definition of ZP, and you can similarly do it with maps Z, like go over all the Z modulo NZ whenever M divides N. So that's just a slightly larger set considered here. And what you get here when you do it, you get called Z hat, which turns out to be isomorphic to the product over all the ZPs. That's a nice exercise. Okay. Sorry? Product topology. And let me pick up exactly what you said, because now I want to connect this constructor with a topological group. So I want to give such an object topological, a structure of a topological group. And so now assume if the GIs are all finite, or if you more generally they could be compact, but we will not need this because we want the profinite. So stick to the finite case. Then this product, and think about the discrete topology for each GI. So in particular, these are compact sets. And so we can look at the product topology. And by Tikhonov's theorem, this is compact. And it's not difficult to see that the inverse limit is a closed subset. And so it's compact. This is closed in a compact set, so therefore it is compact. Each one of them is Hausdorff, and therefore the inverse limit is Hausdorff. And maybe we need to think a little bit to see that it is also totally disconnected. So the definition, second definition, would be that profinite group is the inverse limit of finite groups. These definitions are equivalent. And while we are here, so the inverse limit is also called the projective limit. And so now that's really what we are doing. And if we are here, we can also define what is a propy group. Is profinite where the GIs are all P groups. Can you give me an example? Propy group? Sorry? ZP. Yeah? Okay. We have a propy group. And the third definition, which is also equivalent, a topological group is profinite, third one, if there exists neighborhood basis with the identity of normal open subgroups. That's another definition, also equivalent. So now let's see a few examples. Sorry? Oh, excellent question. Let's prove that they are finite index. So suppose, sorry? It is compact because it's equivalent to this definition, and this definition is compact. But for this one, I don't assume compact. So observation. Suppose H in G, even just a subgroup, is open. Then I'm claiming that it is closed and it's a finite index. Because if this is open, then the cosets, the other cosets, they're also open. So we have a union of open sets that cover the group, but the group is compact, so there's a finite subcover. So there are only finitely many cosets. So it is finite, and these cosets, there is a finite union of open sets. So it is open. Therefore, the complement, which is H, is closed. Right? All the other cosets are open. There are finitely many of them, and so H is closed. I'm in the profinite world. At some point I said. Oh yeah, okay. Okay, yeah. Okay, sorry. Yeah, thanks. Let's even say Hausdorff. Okay, yeah, thanks. So let's see some examples. So the first example is when we look at GLD ZP. So we look at D by D invertible matrices over the p-adics. So firstly, one can show that this is the inverse limit of GLD Z modulo p to the kz with the GLD with the obvious maps between these groups that will give group. And a basis of open normal subgroups will be of the form I plus P D ZP. So okay. So this is exactly the kernel, the map from GLD ZP, GLD Z modulo P to the K. This is a basis. One. Sorry? D by D matrices. So I'm looking at GLD. This is D by D invertible matrices with entries in ZP. This is the inverse limit over all these finite groups. And MD is D by D arbitrary matrices. It's the identity matrix plus this something which is small. See, P to the K is small. So this set, this group, this normal group, converges to 1, shrinks to 1 when K goes to infinity. This is a basis neighborhoods at the identity. Other questions here? This is crucial because probably this is the main example that only one needs to keep in mind, this example, in order to understand what's going on later on. So please ask me now or later just to understand this example very well. Second example is so suppose L over K is an infinite Galois, and the Galois group of L over K is a profinite group, and it is isomorphic to the inverse limit of all the groups of the form F over K, where we run over F K L is finite Galois. So these are all finite groups. And I need to tell you what are the maps. And so if F1 is contained in F2, then the map will be whatever you think be. So from Galois of F K Galois 1 over K given by restriction. So we have compatible system of finite groups with maps in between them. We can just repeat this construction, and is isomorphic to L over K. Right. So now I want to use the remaining time to discuss representations of these groups. So these lectures, I will be only interested in complex representations, and I want them to be continuous. So, the definition, if G is compact, and a representation G is a homomorphism from G to GLV, where this is a Hilbert space and these are invertible continuous linear maps. And although I will not say this every time, there's a continuity that we will always require. So I will not say continuous representation, but we want them to be continuous, which means the map from G cross V to V, sending GV, so V, this is continuous. And I didn't say profinite. This is for compact groups. Yes, yes, that's right. Right, exactly. But as you let me avoid this discussion because this will take us far away, because you'll soon see that we are going to descend to something much simpler immediately when we say the word profinite. But the inverse is, well, you can define it like this, can't you? You can. Okay, so few things that I want to say. Sorry. These are unitary. One needs to prove that, but they're automatically unitary. So that's why I said you can always put them inside unitary group of the Hilbert space. If rho is irreducible, then the dimension of V finite. And the Peter-Weil theorem says that every irreducible representation occurs in L2 of G. So this is L2 of G with respect to the Haar measure, which is a probability measure. That's a representation of G. It's a unitary representation of G. And every irreducible representation occurs here with multiplicity, which is exactly the dimension. It should be familiar from the finite group. So with multiplicity in V. So in a way, compact groups, they behave morally like finite groups. But for profinite groups, we can say a little bit more. So if G is profinite, so the position if G is profinite, and O from G to GLV irreducible and therefore finite dimensional, then O factors to a finite quotient. That is to say, okay, let me start the proof. I'll prove something today. So suppose we have a map from G, GLV. Now we already know that this is finite dimensional. So I can think about this as GLDC or some D. This is rho. Now there's a tension between the topologies of the profinite group and this B group. G has so many subgroups, normal subgroups close to the identity as much as we want because of definition 3. We have many subgroups close to the identity. Every open subgroup contains a normal subgroup. On the other hand, GLDC doesn't have small subgroups. So you can always find a neighborhood of the identity here that does not contain subgroups. Think about GL1, just to have in mind. You can put a circle around 1, and it will not have subgroups, and you can easily see that this is true for GLDC. So pick a neighborhood with no subgroups. Now this is continuous, so let's look at the inverse image. Here is a neighborhood of 1. This is an open set, so it contains 1 here, contains some open normal subgroup, which necessarily is of finite index, as we saw. Now, this subgroup needs to map to a group. There are no groups here, except 1. So this subgroup N must go to 1, therefore it is in the kernel. And so we have the canonical map from G to G modulo N. And this is the kernel, so we can find a row bar such that this representation factors through. Okay, so representation, because of this balance of topologies, representation of profinite groups, they always factor through finite quotient. So to say that we want to know continuous representations of a profinite group is nothing but saying that we want to understand the representations of these quotients. So, yeah, so there is a basis of neighborhood of the identity which is built from open normal subgroups. And so the inverse image of this open set here must contain some subgroup from this basis, and this is subgroup. It must map to the identity here, and therefore it's in the kernel, this map. Okay, so this is that's the proof of this statement. Any questions? Right. And so you can think about a profinite group as given to you by some other problem, like you have it here. And then you might want to use this composition or these finite quotients to say something about your original group. That's kind of, you're interested in that, and you use the right-hand side. On the other hand, the profinite groups, they can be thought of as an organizer for a collection of finite groups. So in this case, you may be interested in the collection of these groups, and you let the profinite group organize them all together in one object. And that, in many cases, it has an advantage to think of one object rather than collection, as we will see. Okay,